Hi, welcome to another video. Today I'm going to show you how to build a smart charge relay, like a split charge relay, and a USB charger. So the story behind this is quite a long one, but I'll try and be brief. I wanted a split charge relay to control the dash cams in my car, so as not to take up the position in the cigarette lighter socket and the adapter which I use to charge the phone. So to get rid of the cameras, I thought I'll build a split charge relay, make my own. This is an Omron 16 amp 5 volt latching relay, a PIC 12F1572 microcontroller. I started with this little PIC 10F. This does everything this does, except I figured unless you've got a programmer by Micro Engineering Labs that takes care of the 10F chips, Microelectronica's programmer can't do this, but it can do this. And then I thought, half of you won't want to solder this little chip. This one's just easier. Both about 44 pence each. So it's got a few input and output channels, same as this. And more importantly, it's got a 10-bit ADC and it's got an internal temperature sensor. And so is this, as I say, PIC 12F1572, 44p each plus the VAT. So my friend has one of these in his Transit. I made it versatile. So this is a P-channel MOSFET, stop you blowing the circuit up if you wire it up back to front. This is 5 volt regulator, that's the PIC. Because it's a latching relay, there's two coils, one coil to turn it on and one coil to turn it off. So we've got two resistors, two FETs, pulling the coil, each coil down to ground to turn it on and off. And a small LED as diagnostics, just tell you if it's on or off. These round circles are so you can program it, just hook it up to the programmer and program it. I'll put the code in the show more, and I'll put the circuit drawing in the show more, because this circuit I used again on my later one with a USB charger. So the only thing I didn't think of, so I wanted to get rid of the dash cams, get them out of the cigarette lighter socket so I can use it for the phone. Put this behind the dash, either wire it to ignition or permanent live, doesn't matter. It draws 2 to 3 milliamps when it's turned off, and only draws a few more milliamps when it's turned on because of this LED here. The relay takes 15 milliseconds to turn on. So you're drawing 120 milliamps for 15 milliseconds, and that's it. So this consumes no power once it's switched on and no power once it's switched off. What I didn't think of, if you've got this wired to permanent live and you take the power away, this circuit needs time to turn this relay off. So I had to add this sort of bulk capacitor here, 220 microfarad, 10 volt. That stores enough energy, so if the supply drops, this chip has got enough energy stored in here to turn this off. So designed and built this. I don't know why I put the connector there to orientation, so that's the in, that's the out. And built a little case and printed it. That sits in there. It's a nice snug fit, and the lid clips on. And I've got one of these running the camera on the car. It's been running it for months and I'm really happy with it. But then I thought I still have to mess about with the cigarette lighter socket for the phone, so I thought let's build a USB charger. So this is still the smart relay. Now I've changed to a bigger 5 volt regulator because I'll put the other board in the box now, but this regulator is about 95 pence. This regulator, only half an amp, not 1 amp, is 30 pence, so you get a third of the cost. So although it's bigger, it's a third of the price. So protection FET, stop you destroying it wiring up back to front. 5 volt regulator, same PIC microcontroller, 2 diodes for the 2 coils, 2 transistors, or 2 FETs, LED to tell you when it's on. This is Texas Instruments buck regulator. This is a 3.3 microhenry coil by Worth, capable of delivering over 8 amps, but this circuit, the way it's designed, runs about 3 amps. So you can put anything in here from 35 volts up to 35 volts, and this will drop everything down to 5. And I'll go through this divider in a minute. And then this is another Texas Instruments part. It's a charge port controller for the USB port, and that's out for the camera. So power in through the relay, out for the camera, and then out to charge your phone. Some of these components are put on by JLC PCB, the assembly department. So a lot of the 0603 components were done by them, and so was this. I was having terrible trouble with these blowing up. I thought these were blowing up because they were getting too hot, but it wasn't. I'll show you why on the circuit drawing. So JLC PCB assembled half the components on this. I did the bigger parts. All the 0603 they did, which actually aren't many 0603. They did these diodes. I just did the bigger parts. Yeah, they did this, which is actually pretty difficult to solder. It's a micro small outline with a power pad underneath, and you've got to have that power pad soldered to conduct the heat away from the chip. That's the ground, and that's the 5 volts. And you can either have this switch controlling the 5 volts, or I've got a resistor package there, link it over to the supply. This is the schematic for the first board I showed you in the white box, which is currently in the car. So there's the Mouser part numbers for the connectors. So 35 volts in, up to 35 volts in. There's the divider for the PIC. So 20k and 2k, which means you can run it on up to 35 volts. So there's the on-run relay with the 2 coils, controlled by these 2 FETs, 2 resistors and 2 outputs, and 1 LED. So that's the simple smart charge relay or split charge relay. Right, this is the circuit drawing for the buck regulator. I'll put the documents in the show more from Texas Instruments. Their data sheet says, their drawings are copyright protected, so I don't want to be putting them on YouTube. So I've sort of drawn my own. So this is the Texas Instruments LMR 23630 buck regulator, up to 36 volts DC input, and whatever voltage out you like. Obviously within reason. I think it comes up to near the supply and down to 1 or 2 volts, so it's a really effective buck regulator with few external components. That's the coil you saw on the board. That's a Worth part number. Have a look at the data sheet. There's an example circuit drawing. They use this buck regulator but as a different charge port controller. So to get your voltage out, you simply put a voltage divider here, and there's a 1 volt precision reference inside the chip. So you use the divider here, and when it sees 1 volt there, the voltage stops increasing. If it starts to see higher than 1 volt, the voltage will drop back. If it's lower than 1 volt, the voltage will increase. And to give you a rough idea, put a tanker here, 40k7 there, you'll get roughly 1 volt here. That will drop 4.13 volts, and you'll end up with 5.15 out for the USB. So you take this circuit, then this is different to the example in the Texas Instruments PDF. I've chosen a simpler charge port controller, the TPS 2511. It's got a power pad, so micro small outline package with power pad, meaning there's a tiny pad underneath that has to be soldered. The advantage of using this charge port controller is it has the CS, which is a cable compensation pin. So when the device starts drawing a certain amount of current, the CS via an internal transistor, which is open collector, that starts pulling this line down to ground. So you connect it via a resistor to this potential divider. When the current reaches half of your threshold set by this current limit resistor here, I've got 46K42, which I believe is about 1.1 amps. I forget how I worked it out. Well, the equation's in the data sheet, but I forget. I think I picked 1.1 amps as opposed to 1.5 or less than 1 amp. So a 46K4 resistor will give you 1 amp, forget the 2. When the current reaches half of this 1.1 amps, the CS starts pulling this line down to ground, pulling this voltage down. This will see less here and start outputting more voltage here. So that's the cable compensation. So you can carry on charging at a high current and not worry about voltage drop in like rubbish USB leads. So on the USB port you've got the data minus and the data plus. They connect to the DM and the DP pins, but it's not that straightforward. I'll show you why in a minute. So Texas Instruments have this drawing, those values for this chip, and it's the 20 pin quad flat no lead, although they've now got wettable flanks, which means you can sort of hand solder them. But I didn't want this device because of the difficulty in soldering this, not to mention the power pad was extremely close to the leads. I'd probably short it out knowing my luck. So I chose this device, just easier to solder, easier to work with. So they recommend these resistors for that, and don't say anything about a resistor on the CS line. They do say you have to make sure the current is less than 10 milliamps maximum. But with these resistors here, you're not going to get 10 milliamps through there. Have a look at the drawing and you'll understand. So 10K7, so Texas Instruments have a 10K7, 37.4K and a 5.6K for this chip. So I chose those values for this chip, and with the exception of the recommended operating conditions, 4.5 to 5.5, and this one over here 4.5 to 6.5, both with a max voltage of 7, absolute max. Every time I plugged my phone directly into the charger, this would blow up, and I thought it was a heat conduction problem. It wasn't. If you choose these values and run it straight to the CS pin, that equals bye-bye chip. I've got a little note here. These values are 10.7K, 37.4 and 5K6, and not friendly for the pick and place assembly because these aren't standard values. So you get charged $3 for each resistor. So these resistors, if I go back up to the top now, I actually messed them out. When I put a 1K here, it would blow up. Put a 4K7, sometimes it would blow up, and I thought it was all heat and current. It wasn't. Started messing about with a potentiometer, put a 47K pot here, and it works exactly like it says. When the threshold gets to half of this current limit, so say 550 milliamps, this starts pulling this voltage down, but this voltage can way exceed 7 volts. So you have to put a limiting resistor here to make sure this doesn't pull this voltage down too far. So it's not until I started putting a 1020K that the chip started lasting, and I blew up 7 of them at about £1.15 each from this country. So eventually, although the value I chose was 37.2k, because we've got a 37.4 here, it's sensible to use it again. And with reference to these values, so 10k is a standard component, 3k3 is standard component, so you still need one odd value component. So you have to pay $3 for the assembly people to put this on the pick and place machine. And because we've got that there, I chose it here, although the value I was happy with was actually 37.2k. So you think, well, how does all of this work? Right, so if you've ever tried to charge an Apple phone, or haven't tried Samsung, you'll know you need a decent charger, otherwise the phone will say not compatible. So here's a phone, let's call it an Apple, but Apple, Android, Samsung, tablets. So the phone will put out 0.6 of a volt on the D+, and it watches the D-. If it sees less than 0.3 of a volt, it means it's a standard downstream port capable of delivering 500 milliamps, 900 milliamps for USB 3. If it sees more than 0.3 and less than 0.8, it's a charging downstream port capable of delivering 1500 milliamps. So once it's established that, well, what type of port? Charging downstream port or dedicated charging port. So it then puts out 0.6 volt on the D- and watches the D+. And same again, if it's less than 0.3, charging downstream port. If it's 0.3 up to 0.8, dedicated charging port, 1.5 amps. But obviously dedicated charging port has no USB communication. So this chip, the TPS2511, there's 3 different schemes other than the communication. There's the divider scheme, where you can use different resistors, which I've seen a lot on the internet. It'll put 2.7 on the D-, 2 volts here. That means it's a 5 watt adapter, 5 volts, 1 amp. If it's 10 watt, just swaps these voltages. 2 volts in the D- instead of 2.7, and 2.7 on the D+. It means it's a 10 watt adapter capable of delivering 2 amps. The Chinese telecommunications industry state that the D+ and D- are shorted together, which means less than 200 ohms between the two. They want that standard. Not sure if it's for the phones or tablets or both. So there's this chip looks after this standard as well. And then according to Texas Instruments datasheet, some tablets require 1.2 volts on the shorted data lines. So when they're both shorted together, you have to put 1.2 volts on them to get the tablet to charge. And it says this Texas Instruments TPS2511 takes care of the above 3 protocols. So that, and then the divider, other than that communication up there. So that's how your USB charger works. So before I give you a demonstration, here is the reverse of one of those charging port chips, and that's the power pad underneath. So I don't particularly like the small package, but it's better than the quad flat no lead 20 pin. That third resistor, the 37.4k, that's in Texas Instruments circuit drawing, and that's to control. That resistor runs to the CS pin, charge compensation pin, and that by itself isn't enough. It will blow this device up. This voltage from the buck regulator will exceed the 7 volts and take this out before you've even finished plugging the phone in. Right, so it's drawing no current, as you can see. turn it up to just over 14. Now this voltage gauge is out, but it's set to come on at 13.7 volts. So off at 13, which says 12.9. Hopefully you can hear the click. And that current of 10 milliamps is actually, most of it is the LED. So that will turn the camera on and off when the alternator comes up. If I plug this phone lead in, and I've deliberately not charged my phone so that it draws lots of current, because as the percentage comes up, the consumption starts dropping. There we go, to turn the voltage up. Right, so that current fluctuating is the communication between the two devices, between this and the phone, establishing what it's connected to and how much current it can request. So at the moment we've got nearly half an amp, but that is at 14.2 volts. Don't forget we've got this buck regulator, so the current is actually going to be up near an amp or more. So I've got this other crappy device. I bought this from a supplier in the UK, terribly inaccurate, and when I plug it in, it tells you if the charger is capable of 1 or 2 amps, gives you an approximate voltage, which is actually inaccurate, but the output, it converts the output and slows the charging down. When we plug either my Apple or a Samsung phone in, the Samsung tells us we're on a slow charger. So I'm not happy with this, but I've got no other method of reading the voltage unless I tear apart the lines. So 490 milliamps. Now plug this in, so you don't have to turn it off. This is actually a robust chip once you get the CS resistor right. So if I plug that in, so that's saying it's a 1 amp, 5.13 volts, 5.16, 5.13. If I turn it off, oh, it just went to 2A as I put it down. One A, come on 2A. No, it's not going to do it. Right, let's plug the phone back in. Let's turn one of these lights off so you can see. Right, so that says we are, so 5.1 volts at 1 amp, 1.1, so that's over an amp. But notice the current on the power supply has dropped to 41 from, what was it, 49? So this is reducing the current output. So 37, 39, 4, so 40, so 400 milliamps on the power supply. Now I'll get rid of this. So you see we're drawing an amp on this phone. Get rid of that, bypass it, give it a second. Oh, it was there straight away. See, we're up at 49, so 490 milliamps. So that current is over an amp. But as this phone charges up, that current will go down. And you can see we're charging, got a little plus. And it works on a Samsung. And this Sony camera charger too. The Sony camera charger draws 500 milliamps. Right, so with this drawing 490 milliamps at 14 volts, let's see what's on that USB supply. Got to be careful. I'll take to blow the chip up, but I've got lots more. So I'll move the phone out of the way so I can get in there. watch the power supply as well. We've got 5.1 volts. Hopefully that meter's in shot. 5.10, and the obviously third decimal place is fluctuating. Actually, there was another point which I was impressed with. Texas Instruments circuit drawings, they don't use polarized like tantalum capacitors. They use various multi-layer ceramics, and a couple of them, and I read up on them. They've got a superior internal resistance, so they get rid of ripple and noise. Right, so that's 490 milliamps, so roughly an amp on a regular USB charging cable. Now I'll plug in this USB extension, which is going to be permanently fitted to this in the car. Yeah, I used to think these were terrible chips. I thought they were terrible to solder, kept on blowing up. I thought it was temperature related. No, it's the CS pin pulling the supply down, the CS pin pulling the voltage on the voltage divider down. This was exceeding 7 volts and blowing this up in a nanosecond. So yeah, I'm not impressed with Texas Instruments circuit drawings, because that 37K is meant to be it by itself, but it's clearly not enough. So I've done the homework for you. Just copy the circuit drawing I've done. So right, 1 meter extension. I'll leave off the adapter for a second. There we go. So now we're on a 1 meter extension plus, for whatever this length is, a meter or just under. So we've got less than 490 milliamps. So it's gone down because we've got a voltage drop. But the phone can request more current or more voltage to increase the current. So we had 5.1 volts here before. Right, let's measure this on the extension cable. So here's the power from the board. We had 5.1 before. We have now got, there we are, 5.396. And it's measuring, don't know if you can see, there's a tiny little veer there on the ground, and the positive there. 2 data lines coming to this chip. That's the current limit resistor just there, which I've set to 46K2, which is about 1.1 amps, which means at half an amp the chip select will start pulling that line down to boost the voltage at half an amp, anything over half an amp. And you see there with the long cable extension, the voltage starts coming up. Yet unplug the extension. And plug the phone directly into the device. Measure it again. Ground. See if I can get closer to the camera so you can see. Ground. The positive 5.1 volts. And look at the power supply in the background, 490 milliamps. So 490, which equates to over an amp via the phone. So if I just show you, this is inaccurate, unimpressed. I wonder if any of them are any good. But this was oh look, it's just flashed on 2A there, because this device had selected the appropriate voltages. Yeah, so this communicates downstream and offers a lower charging voltage or lower charging current to whatever's plugged into it. As I say, the Samsung said you are connected to a slow port, or this device can be charged on a faster port. So 2 amp, plug that into there. So we've got 5.17, which is roughly what we had with a meter. So 97, so 970 milliamps. Put the extension back on. $890, 900 and 5 volts. So we've still got 5 volts here, so the phone is requesting more power. And the voltage is coming up to 5 volts here. Unless it's this device, I'm not sure. But you can see, so with this device connected, this charge port comes up to 5.3, was it? Forgetting, I tested it so many times. Oh, 5.4 now, look. 5.41 volts, which exceeds the USB 2 specification. Shouldn't exceed 5.25. But boosting the voltage compensates for voltage drop in the USB cables. So that's how the cable compensation works on a Texas Instruments TPS 2511, and then that's the buck regulator I showed you earlier, the Worth coil, 3.3 microhenry coil, split charge relay. I'm going to go and fit this to the car. Well, it's getting dark, but there's the USB socket. Drilled a small hole. Well, this is the Halford's dash cams I've got. It's a front and rear camera. So if I start the engine, when the alternator's charging, there we go. So I don't have to worry about it. With that latching relay, when it's off, draws about 1 or 2 milliamps. When it's turned on, the relay draws 120 milliamps for 15 milliseconds, and that's it, and just supplies power to that camera. So that's the split charge relay. Means my cigarette lighter socket is empty for the car phone. Right, so here's that first split charge relay I showed you earlier. This was one in the car, and in case you're wondering, this was the lead that comes with the camera. Didn't want to chop it off and wire it to a 5 volt regulator. Want to keep it standard in case it goes wrong. I simply soldered some wires to the end and put some heat shrink sleeving on. So that's the camera plug. So no loose plugs and sockets hanging about in the back of the car. Soldered wires, split charge relay, job done, just forget about it. It's 7:45 now, nearly, and it's pitch black. So anyway, there's the box in the new case. The camera's wired up. I'll just start the engine. There we go. And you might have just heard the camera come on. So that's the phone charging. And that's the dash cam come on. Turn it off. Turn the engine off. There we go. So the phone's charging, and I've stuffed the extension lead behind the dash. I might put a touch of glue on the socket. So that's the normal cord. Sorted. Now I've got a free cigarette lighter socket. So now you know how a split charge relay became a split charge relay with USB port. But the schematics for the split charge relay, the buck converter, and this, the data sheet for this chip, I'll put them in the show more. If you want the STL files for this, or you want the PCB schematic so you can have your own built, let me know and I'll put them in the show more. Or if you want this one, let me know, I'll put it in the show more. So now you know how a USB port works. Thank you for watching.